Welcome back. Now it's time for the third presentation of the Future of Life module, IMSE Drives Plastics Development. And this session is presented together with Covestro, a global PC and TPU resins and film supplier and one of our key partners in the IMSE ecosystem. As you heard in the previous presentation, also, in IMSE structures, we use printings, films, and resins as means for controlling and guiding the light. And Taxotech and Covestro are working in close collaboration to develop and verify resins and films to be used in IMSE products. We are pleased to have our friends from Covestro joining us today, Dr. Fabien Grote, Dr. Maximilian Hemgesberg, and Dr. Florian Stempel, together with Paavo Niskala, SVP Advanced Engineering from Taxotech. And he will first walk us through some IMSE material verification basics. So Paavo, please take the stage.
Thanks, Tua. My name is Paavo, team here at Taxotech. As you have learned from the presentations from Pasi and Lightworks, the IMSE structure enables great possibilities for sophisticated illumination designs. Illuminated parts can be thin, 3D shaped, and easily variable. And like Tommy, Osram, and Melexis pointed out, LED components and how they are being driven is crucial part for IMSE illumination color performance. What then physically ties everything together, enables in-coupling and passing of the light through the IMSE structure is the translucent injected molded light guide between the plastic films. Here, world-class plastic materials are needed, and therefore Taxotech is working closely with Covestro. To elaborate IMSE light guide and material stack a bit further. IMSE material stack consists of the functional plastic film which carries the printed electronics and components. We call this as a B film. Stack often also includes the A film, which is typically hard-coded plastic film, and it creates the final outlook for the IMSE part and can be easily modified by printing. What then combines these films together is the translucent injected molded resin, which works not only as a structural element, but also as a light guide for the IMSE part. This is the magic of IMSE, which enables thin, illuminated structures with freedom in design and savings in total cost of ownership. IMSE can be built as one film or two film structures, and Covestro will tell you more about this. So in IMSE, printed and conventional electronics are combined with plastic technologies. As there are no existing standards for structural electronics material verification, we at Taxotech have created an internal IMSE material verification process to assure that our material stacks obtain appropriate manufacturing yield, reliability, and performance. From performance point of view, we are verifying the structural integrity of the material stack, the electrical performance of the stack, and the optical performance of the material stack. In IMSE material verification process, we make sure that market-driven individual materials, such as the plastic films and injected molded resins from Covestro, are compatible with IMSE process-wise, chemically, and there's a global supply chain available. This is conducted in T1 and T2 process phases. Approved individual materials are built into IMSE material stacks, which are needed in the markets, and their manufacturability is verified through T3 manufacturing build. Reliability is then verified through 3 environmental conditions. 1000 hours of rapid change of temperature from -40 to 85 Celsius, 1000 hours temperature and humidity steady state in 85 Celsius and 85% of relative humidity, and finally in 1000 hours high temperature aging of 110 Celsius. And as earlier mentioned, the structural integrity, electrical performance, and the optical performance of the stack is being evaluated and verified in T3 phase. After T3 review, the information is packaged into IMSE Builder and IMSE Designer products as licensing content. Multiple Covestro materials have been evaluated through this process, and they have been verified to IMSE licensing content. The purpose of IMSE material verification is to ensure that IMSE material stacks perform with high reliability and without having any unexpected issues in the material interfaces in the selected conditions. Verified IMSE material stacks are then used by our customers in specific application areas where the part needs to be tested and validated against use case specific requirements. This is something that many of our customers in automotive and electronic industry have already done with their own IMSE designs. Now our partner Covestro will tell you more about their IMSE verified materials, as well as the collaboration work what we are doing on developing new IMSE compatible materials. Florian, Fabian and Max, bitte schön.
Thanks, Paavo, for the kind introduction and also warm welcome from my side. My name is Florian Stempfle. I'm head of business development for Covestro Specialty Films division here in EMLA, and together with my colleagues Fabian Grote from the Resins division and Maximilian Hemgesberg from the Coated Films department, I'm really happy to present here with our partner Taktotec and would like to showcase some of our resins and films portfolio in IMSE application. But at first, let's have a short look at Covestro as itself. So Covestro is among the leading supplier of high-tech material solution in the world, and basically we operate from three different segments. So there's first of all our polyurethane business, raw materials for rigid and flexible forms. There's our high performance plastic polycarbonate, and last but not least, there's coatings, adhesive and specialties. And that's exactly where I'm from. I'm today representing Covestro Specialty Films business. We are the leading producer of polycarbonate and TPU films and provide our customers with tailor-made solutions of technical films. Having said all this, you might wonder why Covestro as a raw material supplier is interested in IMSE applications. And from our perspective, in-mold structural electronics can really help to solve and support some trends of our modern world. So basically, Internet of Things, big data and human-machine interaction is developing very fast. We will be more and more connected in the future than we are today. At the same time, we want to have smart but lightweight devices. And this is exactly where IMSE can step in. By IMSE, you, for example, can use the part side compared to traditional electronics by up to 70%. Furthermore, individualization will play a more important role in the future. People want to distinguish from each other. They want to have their own style, their own brand. And this, for example, starts with your tailor-made running shoes, but also will continue, for example, in the automotive industry. Thus, the key drivers in the future will also be freedom of design and efficient variant management. And also those 2 points can be perfectly addressed by IMSE. That's why we partnered up with Taktotec already 7 years ago. And since that time, we're having a quite fruitful cooperation and tried to leverage the potential of our high performance materials. Together, we certified quite a lot of resin and films and also came up with different demonstrators and showcases. Here, for example, you can see our latest results, which we did together. Starting from left to right, you can, for example, see the steering wheel we did together for the K-Fair 2016. Here we combined IMSE with film insert molding and an in-mold coating. For the K-Fair in 2019, we were using our macrofoil films and our macrolon resins to create this fully functioning overhead control panel. This device is smart and lightweight and also includes touch and lighting functions. At the same time, together with our partner Arburg, we did this night light demonstrator to show that multifunctional surfaces can be created by film insert molding. On the very right-hand side, you can see our latest example, the Shepherd lock, a smart lock system from PassiveBolt, which is commercially available since mid of this year. In all these examples have in common that polycarbonate plays an important role. And that's why I would now like to hand over to my colleague Fabian, who will explain you why polycarbonate is the ideal material for IMSE applications.
Yeah, thanks, Florian. My name is Fabian Grote from our polycarbonates business. And let me explain you first why polycarbonate is really the only available option for engineering plastics to fully exploit the potential of in-mold electronics. Polycarbonate is an amorphous polymer, which is available in low viscosities to ensure good processability. Polycarbonate is transparent, enabling light integration into IMSE devices, and we will see lots of examples today and also tomorrow in the sessions. Polycarbonate is heat resistant, so LEDs are energy efficient light sources. However, they do become hot, and polycarbonate can actually handle this heat. Polycarbonate is a tough and impact resistant material to ensure part integrity and also long time performance. And last but not least, polycarbonate is dimensionally stable, which is an important property to overcome topics such as warpage. Let us first take a look into transparent polycarbonate grades and specifically into T3 certified products for IMSE. There are two examples here on the slide. It's the Macrolon 2207 and the Macrolon AI 2217. Both products are low viscous polycarbonate grades with excellent flowability. On the right-hand side in the image, you see an electronics carrier film which was overmolded by AI 2217, which really nicely showcases the functional integration of LEDs and electrical components into one functional material stack. Macrolon 2207 is a general purpose grade from our portfolio that offers the properties that PC is really well known for. It works great for IMSE parts with no or only limited requirement on optics, as it has no specific optical specifications. If you do integrate light functionalities, for example, by LEDs into IMSE, and you have demanding lighting products, then AI 2217 is the material of choice for IMSE. It is a high purity material developed for optical parts and hence can actually help to reduce scrap rates during production. AI 2217 is developed to be suitable for film insert moldings and also ensures a well adhesion of coatings. And also looking ahead, this grade actually offers a lot of functional integrations via color in the future, such as topics like translucent black, sensor transparency, or also edge lighting. Now let's take a look into light diffusion products, which play an important role in IMSE technology. On the image on the right-hand side, you can actually see Macrolon DQ5162 in combination with IMSE. It nicely outlines the desired diffusion effect, expanding the bright LED spot in a more versatile light utilization. When it comes to light diffusion in IMSE, actually 2 points are crucial here. First, you want to achieve high lumen output to have an energy efficient device. Hence, you need a diffusion product that offers you the most light output as possible, so the highest transmission. And secondly, you want to ensure long-time performance under harsh LED lighting conditions. And in order to actually achieve these two aspects, a sophisticated diffusion package was developed For the Macrolone DQ product series, you can see 3 examples here on the slide, starting from low, medium to high diffusion. So the DQ5122 is a low diffusion grade, and then going to high diffusion product, the DQ5162. Let us now take a look into the future and get inspired of what could potentially become possible with IMSE. Here it is all about providing unknown opportunities to designers, combining the touch and feel that only natural materials can provide on the one hand side, with the functional integration and also lightweight that only plastics technology can really offer on the other hand side. You see, for example, on the left, a marble and stunning marble and plate finishes. You can see beautiful wood finishes here in the middle, or also on the right-hand side, you can see a vegan leather enabled by InSkin technology, which really has the touch and feel of real leather. The samples shown here are built up actually from a polycarbonate base layer, which is injection molded onto that natural material, and then is backlit from the backside with LEDs. The surface layer provides the impression and haptics really of a solid material, but in reality it is ultra thin, enabling full integration of light effects like logos, icons, or also the animation that I have just shown. The shown stacks here have not yet been realized with IMSE technology. However, it outlines what could potentially become possible in the future. And let us now take a look into how this can actually become reality. The integration of natural materials into a functional material stack will create ultimately new demands regarding material properties. Materials still need to be transparent while at the same time being stiff to avoid topics such as warpage, a unique property combination which is very hard to find in materials these days. The upper image on the right-hand side nicely shows how a part made of a stone veneer plus PC actually tends to warp after taking it out from an injection molding machine. This can be overcome by materials with an enhanced tensile modulus, such as glass fiber reinforced polycarbonate grades. However, traditional glass fiber reinforced polycarbonate has poor optical performance, which is certainly not sufficient for light integration. You can see that on the third image on the right. The newly developed macro blend OM845G, which stands for optical management in this sense, overcomes these hurdles and sets new standards when it comes to glass fiber filled PC blends. It combines a unique property mix of high stiffness and high transparency as essential for these applications. Now just imagine how natural materials in combination with light effects will change the look and feel of automotive interior, smart home applications, etc. All building blocks are at hand now. So let's take the next step and integrate such concept into IMSE. And with that said, I'm handing back to my colleague Florian.
Thanks, Fabian. So far, as we have seen, there are numerous examples that can be achieved by applying our Covestro resins. And in the next few minutes, I would now like to show you that this toolbox can be even enhanced by applying our films. From a films perspective, therefore, let's at first have a look at the general IMSE stack Paavo has pointed out at the very beginning of the presentation. So basically, there are 2 options. First of all, the one film structure we were using for the Aalborg nightlight and which is also depicted on this slide. And secondly, the 2 film structure, which I would like to explain to you in more detail in a minute. In the one film structure, Macrofoil DE is used as a carrier for the pick and place components. The film substrate can be backprinted via standard screen printing processes with decorative and conductive inks. After high pressure forming, it can be backmolded with transparent and translucent resins. Together with our partner Tactotec, we could prove that Macrofoil DE is the ideal material as carrier due to its outstanding forming, optical, and thermomechanical properties. Furthermore, it's fully compatible with standard silver and dielectric inks. In the meantime, it's also T-Dry certified by Tactotec for use in IMSE applications. In the two-film structure, again, macrofoil DE is used as carrier. This time, however, the material is placed on the backside of the part. Again, it's printed with dielectric inks and the electronic components are placed on top. In the two-film structure, a second film is applied on the decorative front side of the part. With the help of this film, the so-called A film, additional properties can be incorporated into the IMSE part. For example, with the help of our macrofoil LM films, nice optical effects similar to those as shown by Fabian before can be achieved. This time, however, the diffusion act, for example, is provided by the film and not the resin. Furthermore, we can also ensure chemical and scratch resistance by applying our UV curable hardcoats from the macrofoil HF portfolio. These are only two general examples what can be achieved by means of our technical film solutions. In order to see what might be even possible in future, I would now like to introduce to you our LM portfolio. Our light management films are available in a variety of surface finishes and thicknesses. Our films can be used to diffuse, reflect, and guide light. Typical applications include lampshades, cover for ceiling lamps, as well as diffusion lens for LED stripes. Additionally, we have in our portfolio tinted version of light management films with closely specified transmission, like for example our macrofoil LM296, which is tailor-made for use in black panel applications. If we now have a closer look at our diffusion portfolio, you can see that we have highly transparent materials with low light scatter in the portfolio, as well as translucent films with a high light scatter. Here in the graph on the right-hand side, the half power angle, which gives you an indication of the level of diffusion, is plotted against the transmission. If we now have a look at the two products in the upper left corner, you see that they both still have a transmission of about 90%, whereas their diffusion properties are somehow limited, which is indicated by the relatively low half power angle. If you now would place those two films on the light box, you would be still able to detect and to distinguish the single LED spots, as can be seen here in the image on the left-hand side. If you go now up with the half power angle, the light is more and more diffused homogeneously. For example, have a look at macrofoil LM228, which is now marked with a red cycle. If you would now take this film and place it on the light box as well, you would achieve a homogeneously illuminated surface, as can be seen in the picture of the left. You are no longer able to distinguish the single LED spots. And exactly this film was chosen for the first experiments together with Taktotech. Again, we were using a film structure, and the macrofoil LM228 was placed on the decorative front surface as a so-called A film. And as indicated by the picture here on the right-hand side, the appearance of the whole IMSE part can change completely. So as you can see here on the left picture, by using macrofoil LM228 as diffusing film, the light is homogeneously distributed and you get a nice effect, which is completely different to the IMSE part without any diffuser, which I put here on the right side as reference. This is only a first example of what might be achieved by means of technical film solutions. And in order to show you what else we can do, I would now like to hand over to Max, who will introduce you to our macrofoil HF portfolio.
Thanks, Florian. So thanks, Pavel, for the nice introduction, and hello also from my side to you guys out there. My name is Max. I'm heading the global business development for coated films, and I'm also heading the mobility segment for specialty films in the region EMEA and LATAM for Covestro. As Florian just now mentioned, we'll give you a brief introduction on what formable hard coats and coated films in general can do for light management and IMSE technology, and how they enable the added functionality that we see in IMSE. Just to give you a short overview about the coated films portfolio, when we talk about coated films from Covestro, we are talking mainly about coated polycarbonate macrofoil film. And there we have two different families of film. One is the Macrofol HS, which is our 2D standard pre-cured material for example, trim applications or display applications. Then we have also, and this is something that we are particularly looking into when we talk about IMSE, the formable hardcoat series, and there especially the Macrofol HF 312 G1 and G4. Now, as you transition from a 2D material into a 3D free-formable material that can be used in film insert molding, and I'm sure you're all familiar with that process. That means you basically use that film, you receive a sheet, you would then print it, customize it in design, form it, UV cure it, and then back mold it or use it for another molding technology to integrate additional functionality. And this is exactly what we see here with the IMSE technology brought to you by Tactotec in a two-film setup as shown on the upper right side of the slide. You basically have Macrolone resin injected in between an A surface, which is then the formable hardcoat, and the B surface, which is the carrier for the pick-and-place components and the circuitry, like Florian before explained, for example, the Macrofol DE1-1. If you remember our demonstrator that we jointly presented with Tactotec during the K 2019 fair, you will have found there the overhead control panel, which is nicely demonstrating the possibilities and the added value of our materials in combination with IMSE technology, meaning customized surface, weight reduction, so the part is very lightweight, and for sure also regarding the geometry and the design, a very slim design with significant depth of draw. Now, what does that mean for even more integrated applications? And therefore, we have to go back a little bit and look at the trends in not only mobility and interior, car interior applications, but also in E&E, appliances, and so on. What we perceive there is that custom light management and customized surface design become more and more important, in their particular, the transition between glossy and matte surfaces. And as you might have seen in the OHCP demonstrator, you can either play around with light diffusing resin, like Fabian has nicely introduced to you, or you use a Macrofol HF film, which you can customize by using an appropriate ink system. So you can actually also implement the diffusing property by overprinting the Macrofol HF, which is a nice method to render the film more versatile. When it comes now to the function integration into 3D IMSE enabled parts, we think that our Macrofol HF family of hard-coated films presents good chemical and scratch resistance in combination with, as I said, customizable design. And given that we also provide the fitting resins for the application, we open up a certain toolbox that enable you to basically, depending on the application, have added functionality provided by both the film and the resin, meaning the film would rather contribute as the A surface to durability, look, and finish. So that means robust aesthetic surfaces, and the resin could then contribute, for example, not only in light diffusion and light management, but also combine that with added functionalities like thermal conductivity, flame retardancy, which is also a very important topic, etc. So therefore, we try to provide a one-stop shop solution to your material needs. As mentioned before, many of our materials have already been 3.3 certified with our partner Tactotec in joint testing approaches. As you can see here on the next slide, the family of films ranges from the Macrofol formable hardcoat HF312 over the DE standard grades 1-1, 1-4, etc., up to our coax grades like the PCPMMA coax film Macrofol SR906. And for sure, this is complemented then by a series of tailored Macrolone resins. As Fabian has also mentioned, there's the AI 2217, or also different other grades that are ideal for light management and implementing or enabling the desired properties of IMSE technology. When it now comes to certification new materials, we talk about a growing catalog of materials stepwise and over time. More materials will become certified by our partner Tactotec. This also depends on the whole process coming from the design over to the material selection, and then new materials are tested and certified as the demonstrators are produced, and as you basically transition into the scale-up and series production phase. One important thing, keep in mind that our partner Taktotech is also providing the licenses for the in-mode structural electronics technology. I give you here now on the next slide a short outlook on what could be the future in light management when you look at the combination of macrolone resin and macrofol film. For example, we've chosen here the symmetric sandwich setup. It's also a two-film setup where you use a macrofol SR906 on both sides, as a and as a B film. The PMMA side is basically facing outside, and in between you basically have a layer of macrolone resin. In this case, we use side-firing LEDs which are placed on the B film, and we play around with the difference in refractive index to make the light propagate throughout the bulk in that molded part. This structure is very attractive. There are for sure technical challenges to overcome, like for example, that the fact that the PMMA cannot be easily coated by certain PUR coatings, for example, in direct coating, direct skinning. This is just one example of the challenges that we think can be overcome by research in the future, and which in the overall, this technology or this selection of materials presents very attractive opportunities for future applications. Summing up, if you look at the partnership between Covestro and Taktotech, I think this is a very good example of a hand-in-hand of materials and process and technology. From the Covestro side, we do not only support you and Taktotech with the selection of the right material, but we have also expertise throughout the whole value creation in the process. You know probably all how many process steps and value creating process steps are involved in producing the aesthetic parts that we have been seeing in this presentation. Therefore, we for sure have significant expertise also in printing, in trimming, like die cutting, punching, etc., and especially for sure in forming and curing and molding technology. So we cover the whole process chain up to the finished part, and this is what we provide as an added value to our customers. With that, I think we're at the end of our talk. I would like, on behalf of my colleagues Fabian and Florian, I would like to thank Taktotech for the opportunity to present today, and also to you guys out there for your attention. And I think now we are ready to answer and take your questions as you like. Thanks again.
Thank you, Fabian, thank you, Florian, and thank you, Max, and thank you, Paavo, for your excellent presentation today. And next up, we have the live Q&A session.
All right, now we are live with Paavo,
Hello.
Florian, and Fabian. Welcome on board. So let's kick off the Q&A session. We have got some questions regarding what about bio-based and recycled materials? What is your standpoint there? And I think this is for Covestro.
Yes, Tua, let me take that question. I think when it comes to recycling, sustainability, well, let's broaden it not only to pure recycling and circularity, but also to sustainability. And I think probably there are 4 steps to look on. The first is where actually the raw materials coming from. And we have excellent examples here at Covestro, like arphenol that we use for our polycarbonate, or even CO2 as a raw material. Then the second step is let's look into production, and what can you do there to save energy during production, or also to use renewable energies. For example, to use electricity coming from renewables such as wind turbines, etc. Then the third step is obviously how does a device or perform economically and ecologically in the life cycle itself. How much electricity or power does it consume? How much energy does it consume? and so forth. And then the fourth step obviously then links into the recyclability, what happens at end of life. And there are technologies at hand already that can recycle plastic materials, such as the CO2 example that I have shown, that you can use what nature actually does to recycle over the CO2 cycle. Yeah. However, it is more economically or energy efficient if you recycle over different streams. So for example, mechanical recycling could be a topic here, or you can think about pyrolysis, smart pyrolysis, enzymatic processes, etc., all of which are in some sense maybe available or definitely under heavy research by companies and institutes worldwide. And I think that's the way to go also here in the future, to find the right loop actually to circular materials. And I think that's also what Covestro is committed for, to become fully circular. I think that's our new vision, and that's where we are focusing our efforts on in the future.
Maybe to add on there, Tuva, so when IMSC compatible sustainable materials are out there, meaning that they are transparent enough, high purity of materials, so we are definitely gonna do verification process on them as well.
Exactly. Thanks, Fabian, and thanks, Paavo. And there were actually a couple of other questions regarding also the recyclability of IMSC. So for those, I would like to recommend stay tuned or subscribe to a newsletter, because we are having a webinar on IMSC sustainability later this year. So that's where we're gonna discuss the topic more. Then we have question. So what are the main limitations for different injection molding resins?
I'll start. So as Covestro guys pointed out, the transparency is important in IMSC, as the illumination is one of our main things what our customers are building, and then the good flowability, which is definitely needed when you're working with films, and on our two film solution, that is very important.
Okay, thank you, Paavo. Then for a perfect chemical match between printed electronics film and plastic part, do we need to have a polycarbonate substrate to be overmolded with Macrolon, or can we choose for other polymer for substrates to be overmolded, for example, PET?
I would take this question. So yes, for perfect chemical match, you would really have to take polycarbonate as resin and also use a polycarbonate film. For example, if you would use polyethylene instead or something like this, or PMMA, you might get problems due to adhesion or shrinkage of the polymers. So the system has to be adopted to each other, and you really need a system which fits to each other. And this is not only true for the resin and the film, but also includes the inks and all the stuff in between. So yes, you need a chemical fit between the materials.
And
maybe
please.
Yeah. Maybe as a short add-on to this, Florian, it is important also to keep in mind that some films have an issue with haze and clarity. If you go beyond a certain film thickness, this might not be an issue for smaller demonstrator parts, but as you try to realize larger stability of the whole part, becomes
I think we're losing connection with Max.
A matter of concern, which requires then, for example, thicker issue with haze and clarity due to the intrinsic properties of the polymer used. So, can you hear me again?
Yes, please go on.
Okay, real time. As I said, the films that if you look into thicker parts or larger parts, then you require mechanical stability, and this requires then in turn thicker films. And long story short, so PET, for example, has an issue if you use it as a film and you go, for example, beyond 250, 300 micron in thickness, then you will see haze starting to emerge from that polymer material, which is an intrinsic property of a lot of PET types. And therefore, you really need a good match also when it comes to the optical properties, for example, especially if you go to optic force, what Florian mentioned, you need a very good and careful selection of the fit between the film and the resin.
One thing from my side, so PET is typically the substrate used in printed electronics, but for example, we might have an application where bendability of the material stack is needed, so then our go-to substrate material is PET, and we might have, or our customers might have a use cases where the illumination is not needed, as we have done previously. So from the chemical point of view, I agree with you guys, but important is that we choose the correct materials based on the customer needs.
I agree.
Thank you, Max, and thank you, Paavo. And will IMSC be available for not only PC, but for other resins such as PP and PBT as well?
Polycarbonate is our go-to material at the moment, like Covestro guys explained the good properties what it has, but of course we are pursuing other materials and we have verified as well. So IMSC as such is not limited only to polycarbonate, but like said, the requirements from the customer and markets define the use case, and we want to verify materials to all the cases what our customers need.
Exactly, thanks, Paavo. And for those interested in the material verification, like mentioned, you can go over to Tag2Tech YouTube channel and check out Paavo's and his colleagues Palvi's webinar on the IMSC material verification to learn more on that. Then I have a question for the Covestro guys. Can the HF 312 G1 or G4 layer be tailored to be used for external automotive applications as well?
Okay, so that's one for coated film, so I take it. So the coating in itself, basically, the question relates to the chemistry of the coating itself on the polycarbonate film. Yeah. In principle, it is possible to withstand exterior weathering conditions. Now, by our experience, due to the HF312 chemistry, we would not recommend to use this film in exterior applications. In theory, adaptation is possible. However, that would require a complete change in chemistry to make it more weatherable. I mean, when we talk especially about mobility applications, usually we talk about not only Florida, Arizona testing, but also scratch and mar resistance, which is another aspect of being suitable for exterior use. So depending on the application that we're talking about, maybe it should be possible, but as of today, the HF312, G1 and G4 are only suitable for interior applications, both in mobility and also in appliances or E&E.
Thank you, Max. And thank you all, gentlemen, for this Q&A sessions. We now have to move forward with the program. So thank you so much for taking part today. And for the audience, if your question didn't get answered, but you would like to get an answer for that, please contact us at tag2techevents.com. And now we have the next presentation starting in just about a minute. So see you guys soon.
Thank you.
Thank you.
Thank you.
Take
Bye.
care.
Bye-bye.
Again, now that you know all about IMSE illumination and the future of light, the design features, materials, and components needed to create and manage light, let's move into the topic of IMSE design innovation. Tactotech has supported Geely in multiple design projects, turning their design visions into functional, mass-producible IMSE parts, and most recently creating a unique seat controller design for Lynk & Co car. And today, we are very pleased to have Andreas Friedrich from Geely with us to present their view on smart surfaces and introduce our joint seat controller part design. Andreas, please, the stage is yours.
Thank you, Tuva. Hi, everyone. Andreas calling in from Varberg in Sweden here. I will start to share my screen. And now, introduce myself first. My name is Andreas Friedrich. I'm a trained architect and designer. I'm originally from Denmark. I now live in Sweden and I work for Geely Design and specifically the brand Lynk & Co. I have a specific role to scout for new technology and innovation that can be used in our future cars. And as such, I have been traveling around the world, visiting different fairs, and I have been to Oulu many times. And here you see a picture of me together with the polar bear in the polar bear pitching event in 2019, this was. I've also been to a printed electronics fair in the Lopec and IDTechX as a speaker a few times. And I'm very happy to be invited here today to talk to you about opportunities and challenges with smart surfaces in automotive. Yeah. So let's do the next one. First, an overview of the Geely group as such. As you can see here, there's many different brands within the group right now. Here within the Geely Auto group, we have, of course, the Geely branded cars in China. And they have created their own fully electric sub-brand called Geometry. Then we have Lynk & Co brand, which is the brand that I'm working for. We have a 400 people design studio in Gothenburg, and our cars are produced in China. And we already have 4, 5, 6 cars on the market in China. Then we have Proton, which is a local brand in Malaysia, and Geely, they own Lotus in the UK, where we have a full design studio in the UK too. And now even the Smart brand in Germany. Within the Volvo car group, we have, of course, the Volvo brand and Polestar. And within the commercial vehicle group, we have LEVC, which is London Electric Vehicle Corporation. This is London Taxi. And here we have Yangsheng. This is electric small trucks in China. Within the new business group, we have Chow Chow, which is an equivalent to Uber. We have Terrafugia, which is a flying car brand in the US. Kiang is electric motorcycles in China. And over here, we have a little bit of nice to have features like universities in China. We have a few racetracks and or other sports facilities, and also a few hotels and so on. So as you can see, it's a quite diverse group of many different brands. And I belong in this leg over here, the Geely Auto group. In Gothenburg, where we have our studio, Geely is right now building a complete campus and innovation center called Uni 3. What you see here in this picture is a rendering of the 2 first buildings that are actually standing there right now. The foremost building there is having our CEFT engineer, and CEFT is China European Vehicle Technology. That's our engineering team in Gothenburg that was supporting us with the platform development for our first Lynk & Co car, and is now focusing on more innovation tasks and are also interacting a lot with the automotive cluster in Oulu. And the building behind here is just being finalized in these days, and right behind that one, you will find our new design studio for the Lynk & Co brand. And this building is being built now, and it will be Europe's biggest design studio only for the Lynk & Co brand. It will be 5 stories, and it's designed by a Danish architect company called Covestro. And as you can see, it has these lamellas that will allow the building to be more open and public in the bottom part, and then it becomes more and more secretive as we go towards the top. So this will be super cool to move into this building in 2022 when this will be ready. So, in the job of scouting for new technology, one could say that I'm not into all kinds of technologies. So, radars and LiDARs and all these things, we have 2,000 engineers that can focus on those parts. What I focus on is design enabling technology, as we call it. And this means that it's technology that will actually enable us to do different designs of our future vehicles, to be competitive and to be different to the competition out there. And in order to keep track on myself in the scouting I do, I focus in these 6 main topics. It's smart surfaces, lightweighting, magic experience, new luxury, health and well-being, and challenge the conventions. So I think most of these are quite obvious, but within new luxury, one of the main focus areas there is sustainability. And within challenge conventions, this is all about doing things different to what we have done before. Now, when I do this presentation live normally, I would then ask the audience at this point, does anyone know what this is? And this becomes a little bit different when we do this online. And now probably quite a few of you would recognize what this is, but I will have to explain. This is a foil. This is a game changer within the surf industry. It is a foil that will allow any surfboard to fly off the water instead of being in the water, which means that you go at an incredible speed and you fly above the water. So this foil technology can be used for windsurfing, but it can also be used for wave surfing and stand-up paddle boarding and even kite surfing now. So foil is a game changer within the surf industry, and it is this kind of things that I'm looking for, something that could be a game changer within the automotive industry. And what I've found so far, and what I think is a game changer, is printed electronics. And you guys in Oulu happen to be very good at this. And I've been visiting the Prince seminars and also the Printocent cluster with Ilkka Kaistu and the VTT team there, and have had a lot of fantastic contacts and new technologies that I've been finding that way. So you could say that within smart surfaces, which is my topic of today, printed electronics is the enabler to many of the smart surfaces. Printed electronics can be stretchable. It is the enabler for thin film solar photovoltaics. It is also the enabler for tinting of windows. It is the enabler for making thin, smart surfaces of any kind, and those things could even be 3D formable. And printed electronics is also the enabler within OLED technology, and it can be used on textile, and it is even a big part of future display technology. So printed electronics is super important and very interesting to follow. Now, a few examples of smart surfaces. This is a French company called Voodoo, a startup that basically is modifying real wood by extracting the lignin from the wood itself and then replacing it with a unique polymer that is their proprietary technology. And by doing so, the original wood becomes to a modified wood that is 6 times stronger than the original wood. It is somewhat transparent, and it's much harder as well. And this material can be even smart due to the polymer that they're infusing into the material. Exactly how they do this, I haven't figured out completely yet, but it's super interesting anyhow. And this, of course, is then also completely 3D formable. So you can do shape the wood in shapes that you would normally not be able to do with conventional wood. And this is also within the area called Shy-Tech. So you won't see the functionality or the information until you approach with your hand and it will be lit active. Another Shy-Tech example is from Panasonic. This is a luxurious business class airplane interior that I saw at the CES show in Las Vegas 2019. This door is with real wood veneer, and this is also Shy-Tech. So when you approach with your hand, the symbols will be lit and you can then interact with the functionality that's inside this door. And once you open the door, inside there was a mirror with a color screen, and that screen was even an interactive surface. And this door was only 4 or 5 millimeters thick. So this is a very, very good example of what you can do with printed electronics in order to create super slim and smart surfaces. Here's another example of Shy-Tech behind the textile. This is from Yongfeng. And it's a fairly conventional technology behind the textile, but yet again a challenge to find the right textile that will allow for enough information to poke through. And also whatever goes on behind here in order to interact with that surface is also super interesting. Here, another example of 3D formable smart surfaces. This is a Finnish company, Kana2, with their proprietary transparent sensor technology that can be shaped and formed and stretched into a deco surface. You could also place soft material on top of this sensor, and this will then still work. So this is also very interesting, what you could do there. And here's yet another Finnish company, Foresiot, with their fully stretchable sensor technology that basically turns any soft surface into a smart surface. So this can be behind leather, textile, whatever. And this is even with force sensing. So you could interact with a soft surface exactly like you interact with your smartphone today. This is also very interesting. And of course, you can do it on a textile as well. And there is many different ways of doing smart surfaces on textile. Some examples here is a German company called Meyer, where they are weaving conductive yarns directly into the material itself. And by doing so, they create the sensoring areas directly in the textile. And then by embroidering conductive yarns, they can then even embroider connectors on textiles, so you can connect the sensoring elements with external devices if needed. Or, of course, you can print electronics on textile, and there is many different companies that are doing this, but then often the ink itself, it becomes like a rubbery print, like we know from printing on t-shirts and so on, and that then doesn't allow you to breathe through the textile. But this company, Pereta from the UK, has an invention where they are using the conductive material on a nano level. So the fibers of the textile is induced with this conductive material, so the fiber itself becomes conductive. And then when the fibers intertwine, they then create the conductive track on the textile. So by having the conductive material on the fiber itself, it allows the textile to completely perform as the textile before the printing, and also to be completely breathable. So this is also a very interesting way of doing it. And you could do smart surfaces on glass as well. Yet another Finnish company, Luminec, with their electroluminescent screen technology that is actually inside the glass. It's part of the lamination process and is in the glass. This is super interesting too, and would enable us to allow all glass surfaces in a car to be interactive surface as well. And with their technology, they can even make the surface smart, so you can interact with it. So it's not only a screen technology, it's also a touch technology. And now recently they figured out how to come around the problems of water or water droplets that will interact with or trigger the sensor technology. So that's also very good. And you could, of course, do smart surfaces on plastic with foil. This is an example from Nisha with Shytech behind a deco foil. And this is then more of a conventional printed electronics that is laminated to the B surface of the part itself. But Nisha is really good at doing super nice surface foils, and we are already using them in our cars today. But this opportunity to even do those deco surfaces into smart surfaces with information that is lit behind the nice deco material is super interesting. And then, of course, you can bake all this printed electronics directly into the plastic itself. And this is the IMSE that I will dive more deeply into. And this is what Tactotec is really good at doing, and where they have their proprietary technology specialist area. So IMSE is something that I found quite early on, and I met with Antti Käärinen and all the Tactotec team. I think it was back in 2016 or 2017. And I've been following their development over the past few years, and I still strongly believe that this is a super opportunity for us as designers. So I will take you through a little project that we have done together with Tactotec, and that we have shown public on different fairs and in different lectures as well. It's a seat control unit that we did with their IMSE technology, and to the left you see a picture of what it looks like today. This is an early version of our car, so the plastic here is not grained, so bear with me, this is a prototype. But here is then what we did with a separate control unit behind a 3D printed cover. And the benefit of doing so is, of course, very obvious, that the control unit that we are using today in our cars is the same control unit that you have in other cars. So it's a kind of a standard part. And that part consists of, it's made up of 20 unique injection molding tools. It's 45 parts. The complete weight of this control unit is 185 grams. And the packaging depth is 38 millimeters in Y. And if you do this now with IMSE instead, it's only 2 unique tools. It's one vacuum forming tool and it's one injection molding tool. And you get only one part. It weighs only 25 grams and it's only 3 millimeters thick in total. Of course, depending on the 3D shape that you add to it. But here we decided to put them as more conventional buttons, and they are recessed into the surface in order to avoid unintentional interaction with the buttons. And then we mimicked the ergonomic layout of today's buttons as well, so the users would feel familiar with how to operate this. And here's a little video. I hope it comes across fairly okay, of how the functions are working. And we did a little test with the hundreds of our designers in Gothenburg, and all of them immediately after a few seconds got how to interact with this. So we think we are on the right track of doing something unique here. As you can see in this picture, the top view of the seat, you see the benefit of gaining millimeters in Y, because normally this is a tricky ergonomic area in car designing of an interior, where you have the buttons for interacting with the seat controls. They are often in conflict with the pocket in the door panel. And you need the clearance there for your hand in order to interact with the buttons. And now by doing this in IMSE instead, we gained a lot of space here. So you can actually give that space to the customer as a usable storage area in the door pocket instead. So this is also another benefit of doing so. So to summarize all of this, basically everything is possible if we talk about smart surfaces. And this is where it becomes tricky for us as designers, because we can do whatever with this technology. And this is where it's also very difficult, because we are not used to thinking of this. And this is where I have an important role to interact with our team back home and explain to them the opportunities with all this new technology. And still, it's a long way to go before we can start to design something that is completely different as well. Also because the way the engineering part of our business is set up today is that we have those guys that are good at sourcing and doing displays, and we have the other team that is really good at doing the buttons and the switches and the PCB boards. And then we have the guys that are really good at doing the plastic parts and so on. But now, all of a sudden, with IMSE, for example, everything is baked into one piece. So who the hell is, who is then responsible for taking care of such a part? That is a bit tricky. So this is also new for our engineers to understand who will actually be working with this kind of technology. Here's a picture of one of our latest cars. This is a teaser car or concept car that we showed in Beijing Auto Show a month ago, I think it is now. And this gives you a glimpse of what our future electric vehicles will look like. And if we go to the next picture here, this is a close-up of the interior of that car. And this is still a concept, I need to remind you on that. But as you can see, this is fairly still pretty conventional and looking much like we're used to. But if we now start to ask these questions, soft surfaces, they could all of a sudden be smart. what kind of functions would you like to have on a soft surface in that case? Or if we turn the question around and say that all the hard interactive surfaces that we have in a car today, they could be soft instead. What would that mean for us as designers? Or if you say that all the plastic parts that are in a car, they could be smart, what kind of functions would you like to have there? And if you then even on top of that add all the windows, they could be smart as well. What kind of functionality would you like to have there? And then you could hide all the functions as well. So it's a fantastic opportunity that you guys have given us designers, all this new technology. But for us, it's a big challenge to make something new out of this. And then we also then have to consider how smart will our future users be? Will they understand all these new things and know how to interact with them? So it is a completely new landscape we are entering, and this is super exciting and really interesting. But whatever we do, it still needs to be obvious what the function of that part is, or that smart surface. And this is where the challenge for us is as well, that we need to do it in an obvious way so our users, they understand what they're looking at and how it works. Yet again, we know that our future customers, they are used to smart screens and smartphones and different ways of interacting with things. But we need to stick to things that our users will understand. And I will end this presentation with a quote from Tim Brown, one of the founders from IDEO. And this is that new tech should empower the users, otherwise it's no idea. So whatever new tech I'm finding now, the challenge is really to make something usable for our users that they will be able to understand. These pictures here is just an example of some new technology that is actually quite usable and quite nice to have. It's a conventional drawer in a kitchen where you normally have handles, and we already now have soft closing and so on, and also some kind of push-push mechanic functions. But now there is electric push-push function as well. I have this at home in my kitchen, and I'm so used to it now. So whenever I go to other places or hotels, I will go and kick the drawers and nothing is happening. So once you are used to this functionality, it's fantastic. And it's these kind of surprise and delight functions that would be nice to be able to create with the smart surface technology. So, thank you everyone. And now back to Tua.
Right. Thank you, Andreas, for your really interesting presentation and all the insights you have about the design challenges and opportunities.
Thank you.
Next up, we have the live Q&A. All right, time for the live Q&A with Andreas. I think you're on the line as well.
Yes.
So, wonderful. Thank you for the presentation again. Now let's head over to the questions. So what are the main strategic development areas for design at Geely Design?
Ooh, which areas? I would say that there are many areas, really. Yeah, it's probably all the areas that everyone else is looking at as well. So interiors is of course super important, since we know that interiors will be a huge part of autonomous vehicles in the future and so on. So this is of course one area that we are super focused on understanding what's going on there.
Yeah, absolutely. And what do you think are the most interesting areas for IMSE in a car?
Ooh, I would say that all places where you could gain space saving as well, and also lightweight opportunities. That would be great. Also with the lighting, as we've been touching upon today, is super interesting. The opportunities of bringing ambient light and different light features into plastic parts. That's wonderful too.
All right, yeah, there definitely are many possibilities. Then there's a question about the concept car that was shown there.
Yeah.
Are there any Shytech technology inside of that car?
A little bit.
Yeah.
I'll say too much.
Okay, so remains to be seen. So I guess stay tuned for the audience.
Yeah.
Okay. Then there was a really interesting question about the Capsen Solutions tactility and usage with gloves, since we're up here north and it's winter time. So the using gloves can be somewhat tricky, or using touch surfaces with your gloves on. So how much is this kind of localization taken into account in your projects or in your work?
This is where I normally would say that I'm just a designer.
Yeah.
I need the engineers to solve all these kind of issues, but I definitely see the problem, and it is with also tactile feedback with a capacitive touch is an issue that we are discussing quite a lot. How can you implement different capacitive sensors and then still have some kind of tactile feedback? And I know you guys are working on this as well, and we are discussing this, and it is a topic that is super interesting. But for instance, with the seat controller now, the whole seat was moving, so you got an instant complete feedback of what was going on. But tactile feedback is an important part of automotive, and it needs to be dealt with in the future too.
Yeah, absolutely. I think the smart surfaces are becoming more and more common in pretty much all the environments that we are now in. And for the audience, a reminder, please use the Q&A box for your questions, so we can find those there. Continuing on the different geographies and localization design that you have to take into account in your projects, are there some other considerations you have to make when designing, or do you have some examples in mind?
Oh, you mean the difference between Sweden and China, or?
For example, like if you are working on a project.
Well, it's been an interesting journey, and the Chinese customers is very picky with the details and intricate ornaments and so on. So this is something that we are used to working and understanding how they think about good design. So of course we look into different areas of the global aspect of different customers and so on.
Yeah, exactly. And as another question for you as a designer, so how and where, in your opinion, do you think are the automotive industry shifting towards to?
In which direction it's shifting?
It's a pretty broad question, but maybe considering like design features in a car, let's say.
Yeah. One thing in the future is that the steering wheel will be gone, probably, and that is a challenge, and people will maybe be moving around differently in the interior and sit differently. So this is definitely one challenge and shift that we see is slowly coming.
All right, thank you. Okay. There's also a question on the if you have an IMSE project on the exterior part. This might be confidential.
I can't really say anything about that right now. But for sure, IMSE is super interesting for exterior as well, due to that the electronics is encapsulated, and that gives us a lot of new opportunities, I would say. So, and also with the light, it's super interesting too. So, yeah.
And we'll see.
Yeah.
Be interesting.
Yep.
Then about the seat control unit that you showed in your presentation, how was the end user's feedback of it?
We haven't got any end user yet in this. This is still a proof of concept that was shown and that we are evaluating. So hopefully we will see something in a future car soon.
Okay, but you tested it with other designers.
Yes.
Yeah.
It was 100 of my colleagues that tried it, and the feedback was really good. Some were missing more haptic feedback, and that is of course those people that are working specifically with haptics. That is their area of competence, and therefore they of course are asking for more haptics. So that they could feel with the whole body when the seat was moving, so they had the full haptic experience, I would say. But of course, yes.
Yeah, exactly. And now that you mentioned the Haptivity, tomorrow we have a presentation regarding Haptivity. So for those interested, please stay tuned tomorrow to learn more about that. All right, I think we have to now move on with the program. So Andreas, thank you so much for joining.
Thank you
today and for your wonderful presentation.
Thank you.
And next up, we have the joint presentation with Covestro starting in about 8 minutes. So please stay tuned.
Thank you.
Thank you.
After design innovations, it's now time to look into manufacturing of IMSC. As today's last, but definitely not least presentation, we will hear about automated mass production for IMSC, Case Aalborg film insert molding. And this is a joint presentation by Annika Müller from Aalborg and Marko Suo-Anttila from Taktotech.
Hello.
Hello.
And they will walk you through the IMSC mass manufacturing capabilities and present the jointly developed, highly automated injection molding mass production cell, which was introduced at K-Fair 2019 in Germany. And Marko, please take it from here.
For the beginning, I'll walk through the IMSC manufacturing process on high level and split into the 4 main steps. First step is screen printing process, in where decorative, conductive, and dielectric inks will be printed. And during this phase, we will create the wirings, sensors, antennas, contact terminals, and other IMSC relevant electrical features by printing. Once printing step been completed, there will be a surface mounting process, and during this process, electrical components compatible for IMSC structure will be picked and placed into a film. Interconnection is made by using the adhesives. So after this process step, there will be a curing for adhesives, and once the film being cured, there will be a functional testing for a film. During the third step, this flat film with the components will be 3D formed, and it will get the 3D shape. Once this being completed, thermoforming process, these parts will be cut to smaller pieces or laser cut or die cut, so that the film itself fits into a tool during the molding process. Step number 4, which is the final step, will be the injection molding process. And during the injection molding process, 3D formed film will be placed in a tool as an insert, and the final part will be molded. Once this being completed, this part will be electrically tested and it's ready to move to the next phase. And during today's presentation, Aalborg will cover more about this step number 4 during the presentation. And next, I'll go through IMSC part structure. These materials, what we use for the IMSC structure, is verified by the Taktotech, and it consists of materials such as decorative A surface, which carries a film or other film-like natural materials, and decorative inks, which is on top in the picture. Functional B surface, which carries conductive inks, dielectric inks, and SMT electronic components, such as LEDs, for example. And as in this picture, there is a resin, plastic resin in between of A and B surface. And this is something what we call as a two-film structure. So there is a film underneath and the top, or front and back side. But this can be also one film structure, so that either A surface or B surface act as a decorative surface and functional surface at the same time. In today's presentation, we are talking about the one film structure type of application, where A surface carries decorative and electronics properties as back molded part. The part what we used to create this automated manufacturing cell together with Aalborg was named as Nightlight Demonstrator, and I'll describe a few design features of this part. Decorative part of this part consists of black and white decorative surfaces for logos, user interface elements, and illuminated window, and the backside in the middle functional surface which carries conductive inks, traces, capacitive sensors, and 5 pieces of LED components. And this manufacturing demonstrator, what we used to create this production cell, was designed by Tactotec and in collaboration with partners such as DuPont, Covestro, Everlight, Cypress, and some other parties. Film insert, as seen in the picture, is on 3D shape before molding, not on a flat level. It is recommended to form this film before the molding to achieve electrical, aesthetic, dimensional, and electrical characteristic stability. Insert term being used as feeding into a tool is not from the feeder. Typically, it is by the robot. And that's why film will be placed into a tool as an insert. Due to the sensitivity of electrical components, printed sensors, traces, LEDs, it is important to consider proper part handling to avoid part handling related defects. In this specific case, robot gripper, trays, and other equipments were developed in collaboration with Arberg to make this part handling as robust and error-free as possible, to make sure that the sensitive components, conductive traces, and sensors are not harmed during the process. Injection molding for IMSE follows in general the common injection molding principles, especially for film insert molding type of molding process. Typically, the considered items are related to injection molding gate location, its type and size, how ejector pins are located, how to consider the parting line, and so on. We also need to consider sensitivity of the film, how to grip that before molding, and once the part been removed from the tool, how this part will be handled so that there will be no handling related defects, for example, for the testing process. For all of this, Tactotec has developed additional know-how and expertise, and it's been packaged into the so-called IMSE Builder, which is one of the products which Tactotec licensed to its customers. In today's presentation, Tactotec and Arberg will present highly automated injection molding mass production cell, which we introduced 2019 at K-Fair show in Germany. This production cell was developed together with both companies' ecosystem to demonstrate IMSE manufacturing mass production capability by using the modern efficient manufacturing system which is available today. We also demonstrated that IMSE manufacturing does not really require uniquely developed manufacturing processes or special capabilities, hard to find or develop. Solution is available today. It can be modified, developed, and used for the certain specific products, company and industry requirements. If you would like to see the complete IMSE process running and to see Tactotec manufacturing line and other IMSE related information, please visit at Tactotec YouTube account or our website to get more information. And I would like to thank you for your time and attention. Annika Müller from Arberg will continue the next. So Annika, stage is yours. Thank you.
Thank you, Marco. Hello from me too. As already mentioned, my name is Annika Müller, and I'm working for the application engineering team of the company Arberg. On the following slides, I'd like to inform you about the application with the IMSE, which we had on the K-Show together with our partner Tactotec. However, at first, I will start with a few information about Arberg. On the picture, you can see our headquarters in the Black Forest in Germany. Our headquarters, with an area of 180,000 square meters, is the only production site of the company Arberg. In 2019, we had a consolidated turnover of 738 million euro, and our export share is about 70%. Worldwide, we are 3,200 employees, and approximately 2,600 of them are working in the headquarters. Arburg is present in more than 100 countries around the world. In 26 of these countries, we have our own subsidiary. These are marked on the map with the red dots. In the other countries, which are marked with the yellow dots, trading partners represent us. Arburg is a family-owned company, which was founded in 1923 by Arthur Hehl. Later on, his two sons, Eugen and Karl Hehl, took over. Nowadays, the third generation of the family Hehl and Keinert are the managing partners. Our main product are the horizontal injection molding machines. On the picture, you can see one example of them. They are available with a clamping force from 125 up to 6,500 kilonewton. And the part weight, which can be realized, goes from 0.001 up to 4,270 grams. But there are also some special machines. For example, the vertical machines, the rotary table machines, the cube machines, and multi-component machines. We also provide complete production cells together with our machines. You can see such an example of a production cell on this picture, and later on in more detail at the IMSE application. For such a turnkey solution, Arburg is the primary contractor for the customer. This means only one contact person for everything. We have more than 25 years of experience in technology consulting, and the system services are available worldwide. In such a project, we are already involved during the product idea. Then, after the definition of the requirements with the customer, we prepare a concept and have an assessment together. After the planning and the building, there's a fully functional test here in our headquarters, not only of the machine, but also of the complete automation. We also support the customer with service during the installation on his side and during the production later on. Our customers are from every sector of the industry, and we also have special experts for these branches to support the customer on the best way possible. To give you a short overview, here are mentioned some of the branches. We also have experts for injection molding for special materials, like silicon processing or powder injection molding, and also for special processes, like micro-injection molding, injection compression molding, and film insert molding, which leads us to our cooperation with Tactotech. And you can already see a cutout of the part in the picture in the middle on the left. Here you can see a complete picture of the part, the nightlight. To give you a first impression of the part, here are some facts about it. The diameter of the part is 128 millimeter, and it was produced in a one cavity mold. The part weight is 49 grams, and the foil was overmolded with polycarbonate. The nightlight is a sample part to show how functional 3D touch foils can be used for the more and more upcoming digitalization. For example, in the automotive interior. The application was running on an electrical arounder 470A with a cycle time of 65 seconds. In this case, we overmolded the backside of the foil where all the electric wires and LEDs are located. On this picture, you can see the complete production cell on the K-show. The automation was placed in a clean room cell and equipped with two laminar flow boxes. The first one on the machine over the mold, and the second one over the automation. Through the clean room cell, we can minimize the contamination of the foil. I go into more details about reason later. Here you can see a top view of the machine and the whole automation to give you a short impression of the installation. On the top of the picture, there is the machine with the mold, and you also can see the laminar flow box. Located on the left side, we have the cleaning station, beneath the centering station and the testing station. In the middle, there's the multi-axis robot, and on the corner on the right, the tray server. For this application, we used a high-precision electric machine. And with our machine controller, we can control all the complex processes, not only of the injection molding machine, but also of the automation components. In the mold, we had special film holders to ensure the foil remains in the correct insert position, also during mold closing. And there was also additional mold centering in the mold parting. At first, the completely integrated multi-axis robot has to pick up the pre-produced foils from the trays on the tray server. After this, the foils have to be placed in the centering station to get the correct alignment, so they can be handled with high precision during the whole process. After the correct positioning of the foil in the gripper, it needs to be cleaned. This step is necessary because there can be some contamination of the foil surface, for example, through particles in the environment. And if we don't clean the foils, the particles will cause small visible markings on the surface of the finished part. In case of the IMSE foil, we used ionized air for the cleaning. You can see it on the upper picture. Another possibility is to use a brush. The cleaning method must be specified for each application individually. One benefit is the cleaning takes place during the injection molding cycle of the part before, and therefore it has no influence on the cycle time. After the cleaning of the foil, the gripper inserted into the mold. To handle the foil, we have the possibility to use vacuum or gripper technology, depending on the requirements of the part, or in this case, the foil. Here we used some vacuum cups and sucked up the foil on non-critical points. We also had a centralization between the gripper and the mold to support the perfect insert position. During this step, there is also the possibility to clean the cavity for the next cycle, if this is necessary, for example, from deposits. But it wasn't for this application. Simultaneous to the insert of the foil, the overmolded foil is removed from the mold. We insert the foil on the movable half of the mold and remove the finished part from the fixed half of the mold. After removal of the part, it was placed into the testing station, the white box in the middle of this picture. There we had a 100% quality control of the electric functions. Also, other post-processing steps can be added at this point. For example, the removal of a sprue. So with this machine and automation, we have a safe, reproducible, and economic production for the nightlight. And when the parts leave the automation, there are no post-processing steps needed. They are ready to use. To bring all these single steps in one automated cycle, we'll now have a look on the film of the application. To summarize all the important points of the presentation, I put them together into this tech cloud. And as you have discovered, we work together with the customer or the partner from the beginning of the product idea and also during the production. We participate with our experience, our know-how, and our support throughout the whole time, and it doesn't matter where the customer is. Thank you for your attention.
Right, thank you, Marco, and thank you, Annika, for your excellent presentation. And next up, we have the live Q&A. And now we are live with Marco and Annika.
Hello.
Hello.
Okay, now.
Okay.
Hello.
Hey, Marco. So, audience, please send in your questions via the Q&A box. And we'll now start the Q&A session. And the first question we have is for Marco about the IMSE yield levels. What can you say about those? What are they? Can you give any typical numbers?
Yes. First of all, we are using for the technology mass production equipments and the environments. So expectation, of course, should be on that side and that level. Our own experience based on the requirements what we have today varies in between from, let's say, from the level of 90% to upwards, but we do have also some yield levels which are below of that. And now the important question here is that what are the customer requirements in the end of the day? What is the complexity of the design of the part to be produced, and what kind of use case will be done? So there is no one single number, but let's say the industrial numbers typically to be expected all the way. And so far what we have done in our own production, the numbers are cost-wise and the performance-wise definitely reasonable and something which makes completely sense for the mass production environment.
Okay, thank you, Marco. And then the next question, I think this is for Annika. What was the most challenging part in designing the automated cell for the IMSE part?
I think one challenge was the reconciliation of the gripper with all the automotion components, because in this case we have this high quality foils which we have to handle during the whole process, and with the LEDs on the backside and also the electrical tracks, we have to make sure that we don't damage them through the handling. And so I think this was one of the challenging parts with this automation.
Okay, so there definitely are quite a few things to consider when putting together a cell like this. Thank you, Annika. Then about this is related to the IMSE technology, like some general production rules. What kind of general rules are you following in order to avoid damaging or displacing of the LEDs while thermoforming?
I think that one of the key rules there are really related to handling. Once you load and unload these films during the process, it's really difficult to damage those LEDs by the equipment or the machinery, because the forces which are used against the film comes from the gas. And that's why it's pretty gentle process for the components itself. But what we have seen is probably the handling of the film once you load and unload, and those needs to be done carefully. And probably then how do you transfer the films to the process itself and out from the process. So we are using the stacking and the certain kind of layerings for the films so that those are not touching each other, as an example.
Okay, and to continue on that, what kind of methods are there to hold the film in the mold firmly? during the process?
Multiple. Mechanical holding is one thing. I think we used mechanical and vacuum holding both in this Arberg cell tooling, so you can hold mechanically the film, and then you can use a vacuum. Most of the cases we use vacuum or combination of mechanical and vacuum holding.
All right, thank you, Marco. Then a question about the manufacturing cell. Could it be adapted to a different production part, or does it need to be rebuilt completely?
Depends, because, for example, the centering station and the cleaning station and also the trays were specified exact for this application, but with some small changes, it can be more or less adapted to another application.
All right, thank you, Annika. Then a couple of questions regarding the cell indeed. How can the removal of the sprue be added in the clean room because of the possible contamination?
If we had to add a post-processing step like the removal of the sprue, where we had to do some milling or trimming, there's mostly an encapsulated cell in or next to the clean room cell. So we put the finished parts, in this case with the sprue, in this extra cell, and remove the sprue, for example, in this extra cell to minimize the contamination from the trimming, for example.
Okay, thanks, Annika. And then about the nightlight demonstrators, how do you avoid having circuit breakage between the injector body and the connector tail?
Sorry, could you please repeat that question again?
Yeah, about the nightlight demonstrator, how do you avoid having a circuit breakage between the injected body and the connector tail?
In this case, this was done partially by selecting the inks certain way, and this ink selection is not only about the conductive inks, but it's also the other inks carrying the conductive traces. This is the one thing. Also, there has been the certain little let's say trimming type of activities done on the tool side also to avoid. I believe that the meaning here is that there is not like cutting type of effect on the edge. So it's a combination of this film design, selection of inks, and also the tool design on that specific area.
Okay, thanks, Marco. Then we have a question about the cycle times. What is the current cycling time for this demonstrator Arberg was showing? And then a continued question on that. What is the biggest size to produce IMSE parts?
The cycle time for this application was 65 seconds. We could have done a little bit more optimization, but we stuck to the 65 seconds because of quality of the part. And the maximum size, it's not really a definition or regulation from our side, maybe from the IMSE side. But you have to keep in mind that the foil, if it gets bigger and bigger, is not so stable anymore. And if you have to do all the transport from the tray to the centering station and forward, you have problems if the film is not stable as it was on this application.
Yes, maybe I say a few words about it. We don't have absolute value for the size, that what is the maximum size. Definitely, partially it is driven by the design, like how complex the geometry of a part, for example, is, and so on. But then there are certain, let's say, rules which are good to understand, like conductive inks conductivity. So if the traces comes very long, for example, then the conductivity of those inks can come to a limitation. Then machinery at some point during the process might cause certain limitations, let's say surface mounting, for example. So the surface mounting machines typically can take certain width of the film, and length can vary. But then if you look at injection molding, for example, then you have a more flexibility and sense of the sizes for the part. But anyways, currently we are not talking about that the IMSC should be used for the roofs or car bumpers. Those are way too big parts for the technology today. If I say roughly some size consideration, I would say in a car, let's say automotive world, something like center console stack size of parts, overhead control panel, for example, door trim sizes like as such, depending on the functionality and the requirements, could be considered for sure.
All right, thanks, Marko. Then another question for Annika about the cavities. So how can the cavity be cleaned?
There are different options. For example, you can use ionized air, which is, for example, added to the gripper itself, or you can use a brush. Normally such a brush then would be mounted to some side of the mold, or for example, a CO2 jet. It depends on the sort of the deposit, and also it's normally not needed every cycle. Sometimes it's needed every 10 cycles, sometimes only once an hour. So it depends on how often it's needed and what deposit you want to clean the mold from.
Okay, thanks, Annika. Then we have a question regarding the IMSC manufacturing process. So does the screen printing, does it have to be done in the same plant than the SMT and the injection molding?
Our proposal is that the screen printing and surface mounting preferably should be done in the same location. And why it is so? There is for example, in the case of the problem solving or potentially adjusting something for the surface mounting or pick and place process, it is much more easier done those in the location where screen printing and surface mounting are located. Those both are typically also in the electrical manufacturing type of environment, so the fit together is kind of quite a natural, but the molding doesn't need to be necessarily in the same building or same plant. Naturally, it's a sensitive film, so the handling comes then more critical. So if the film itself needs to be delivered different location, then you need to consider the packing and handling more carefully.
Thanks, Marko. And then another question about the nightlight demonstrator. Are there conductive adhesives used in this demonstrator?
Yes, LED interconnections are made by two different type of conductive adhesives. Yes.
Okay. And then about the temperature. How about the temperature inside of the IMSC part after a long time running? I think this is about the temperature during the process.
During the manufacturing process?
Yes.
I believe that the most highest temperature will be introduced during the injection molding process. Let's say like if injection molding resin is polycarbonate, like we many times use, then the temperature at some point as a peak value will be around 200, let's say 70, 80 Celsius centigrade roughly for the moment. And then it comes down due to the cooling. Processes before that will be lower temperature. So thermoforming is around the TG point of the formed film, which is somewhere around 160 Celsius centigrade roughly. And then if we go to the curing for the inks, those are low temperature inks. So we are talking about 80 to 100, something around there. And the curing of inks curing of adhesives after SMT or pick and place process is also low temperature process, which is around 100 Celsius centigrade roughly. So injection molding obviously increases the temperature of unit in the last step most highest.
Thanks, Marko. And then another question for Annika. So which classification is needed for the clean room?
It's not a clean room as for medical applications. There is no certification needed, but we need like the ISO 8 or 9 for example, medical application. If the IMSE application is no medical application, if it is a medical application, it's also needed. But we need this clean room because of the contamination I told before. And there's also no FDA certification, for example.
That's correct. So I'll add there that IMSE itself does not necessarily require clean room environment. It really comes from the industry and the application requirements. So as Annika said, if, for example, this application will be used for the medical industry, indeed, there probably will be even some other requirements what needs to be followed. We prefer to produce at Tactotec in clean room environment due to the multiple reasons. First of all, we can keep the environment stable, which always helps in any case. And secondly, we are also making there the sensitive electronics, sensors, and so on. And those are sensitive for contamination and dust and particles and so on. So to avoid the defects which comes from the flying dust and the other particles, then of course clean room type of environment helps and it makes this kind of problems easier to handle and less issues during the testing and so on.
Okay, thank you both. Then can we place the film in both half, cavity and core, in the same time and then inject the resin into mold?
Well, I can say that yes, we call that as a material stack. So the materials are stacked in a certain way. Film can be on the front side of the part or the back side of the part, and that once we go into the molding process, yes, it can be placed into a tool, both cavity and core side if needed during the process, also automatically. And by the way, we do have one customer also available who have built this kind of automated cell already, and it's completely possible and doable process. And then injection molding will be in between the films if there are two film structures, so film is on the both side of the tool.
Okay, and let's take a couple of last questions and stay in the scope of IMSE manufacturing process. So what is the maximum injection pressure that can be applied during the IMSE molding process?
Same pressures like for any other molding processes. So, for example, if there is a need to achieve certain, like let's say, cosmetic requirements or aesthetic quality, or reduce the amount of sink marks and keep the dimensions and so on, you need to apply similar pressures like for any other plastic part to achieve the similar effects. And currently we are using the pressures which can be applied to any these approved materials like polycarbonate, what we use, all the range, whatever is giving the needed results for the final quality and the functionality of the part. So we don't have any maximum minimum type of value for the pressure. There is one consideration, of course, but we are taking care of that before the molding, and once we approve the material stack, is that we should use the components in this structure which really can withstand those pressures. And that's critical, of course, so that the pressure applied during the molding is not harming those components inside.
Okay, thanks, Marko. And then the final question we have time for: how are the conductive adhesives applied? Which techniques are used?
We are using dispensing during the surface mounting process. So there are dispensing units. We are using currently hybrid machine. It fits for our purpose. It doesn't need to be like that. It can be a separate dispensing unit before pick and place, and then continue by the placing the components. But currently there will be a dispensing nozzles which apply the glue or adhesive to the film, and those kind of equipments and the adhesives are commonly known in the industry and available nowadays for anybody who is interested about this.
Okay, thank you, Marko, and thank you, Annika, for this Q&A session and for the presentation as well.
Thank you.
Thank you.
All right, bye.
And
Bye.
now it's time for us to wrap up the day one of the IMSE Days. And we really had a great day full of interesting insights in the world of IMSE and the design innovations. And for that, a big thank you goes to our wonderful presenters. And also thank you, audience, for joining us today and sending in your questions and joining the event. And unfortunately, this year we won't be heading out for drinks, dinner, and sauna together like in the previous years, but there's always next year. So if you have any questions or comments, for example, your question didn't get answered during the Q&A session today, and you would like to continue discussion, please contact us at tactecevents.com. And tomorrow we will start the session at 10 a.m. EEST, so please make sure to stay tuned and please use a separate link for joining tomorrow. And I wish you all had a great day with us today. I know we did. And I will see you all guys tomorrow online. Have a great rest of your day.